Hi, everyone. Welcome to this session, How Lettria Unlocked 20% Accuracy Gains, presented by Romain Albrand. Thanks for joining us today. And Romain, I'll hand it over to you.
Yeah, thank you. Thank you very much. I just check. Okay, Emily should be okay. So thank you everybody for attending this presentation. I will So this is a presentation about Lettria and about how we managed to gain 20% of accuracy using Qdrant and Neo4j. It used to be a presentation that I've done for a webinar with Qdrant that has been unchanged. And Yolande Perrier invited me. I think Yolande invited me. Proposed me to do this presentation. So thank you to her. So I will first talk about, for those who don't really know, Lettria and our challenges in terms of GenAI and of data structuring. So we have a regulated industry that have serious issues implementing GenAI, mostly because trust issues that I've been facing. These trust issues come from, well, first the LLM errors or hallucinations, and also the phenomenon of black box that reduces the explainability is, of course, important to them and another source of issue. So they want to actually reduce these issues. Us at Lettria, so how do we outperform the existing solutions? We have mainly two proprietary assets. The first one, and we'll talk a bit more in the detail afterwards. The first one is a document parsing library that manages to, well, the extraction of input PDFs of the client. These documents may be endowed with text, but also tables, complex diagrams, images, and so on. And the other one is a knowledge graph that enables to structure the data and request them for different use cases. And we've measured for quite strong gain of performance. And we'll talk a bit more afterwards. So these are the two main proprietary assets on top of which we have built our GraphRAG solution. So the main problems with classic RAG, I will just briefly talk about this before diving more into the GraphRAG. Well, it struggles first to perform what we call a co-reference, that is, create some links across the several documents that we have to ingest, and that will structure the data, the knowledge data. We have a difficulty to perform multi-hop or complex reasoning. They require different elements across the client documents. Also, another problem that I just developed earlier is the lower explainability and the fact that, well, a chunk is quite huge, maybe quite huge for the same amount of information it provides compared to a very structured graph representation. And this, of course, limits the context window used to well, obtain a final answer. So, to sum up, classic RAG retrieves the chunks kind of independently and a bit naively, whereas the GraphRAG structures it, connects a knowledge for deeper and explainable reasoning. So the GraphRAG, at Lettria, we have two pipelines that I will present right after: the ingestion pipeline and the generation pipeline. So some components are, of course, involved in these two pipelines. I just talked about document parsing and text-to-graph and knowledge graph. So there's this text-to-graph extraction process that is based on ontology. We have also some retrieval graph or semantic embedding. And also we make use of smart orchestration that enables to efficiently and smoothly add some components to perform well, more sophisticated reasoning steps in the generation. All these processes may be working asynchronously as well, with some notions of dependence. So it's important to make sure that everything works well together. And this will be particularly the focus of this one of the focus of this presentation, where I will dive a bit more into the collaboration we had with Qdrant and Neo4j. So about the ingestion, quickly, we have input PDF, as I've just said. Document parsing is in charge of extracting the content of these PDFs. We also have, as you can see, a reordering feature. And we also use what we call internally, at least, split candidates. Basically, we just try to evaluate the notion, a notion of ordering in the extraction that we perform, so that afterwards we can split meaningful chunks given a split candidate configuration. So if we want, for example, to have very smaller chunks that are basically used for the part of vector chunks, we actually will use a configuration saying that we want to have smaller chunks. And in order, for example, to build a graph, we would need chunks, pieces of text that are a bit larger. And as a consequence, we will play with different configuration to get the text-to-graph chunks. So all this notion that document parsing provide us enables to split a bit differently. The text-to-graph chunks will be used in the text-to-graph process, also with an ontology that will really provide us some rules in order to build the graph, and eventually we'll build the graph, so graph with relations, node properties, and so on. Both the vector chunks that we've not so far dealt with and the graph will be embedded and stored in a vector database. Qdrant is the one that we chose. And eventually, of course, we will store the graph in a graph database, and we chose Neo4j. In terms of generation, we will first use a process to just perform a kind of a sum up of the possible history of a conversation, if there always has been some question in the past. But basically, from the rephrase query or just an input query, if it's the first one in the conversation, we will perform an embedding, retrieve the chunks and the relations that are relevant using Qdrant, the vector database. And with the retrievation, we will perform an expansion that will provide us a contextual subgraph that will be more exploitable in order to, just feed an LLM context. And this is the final step, where here we can eventually get a final answer. All this process is particularly, has to be particularly optimized. Even though we use like very, very sophisticated LLMs, we measure that, how impactful it could be to really make them concise and well structured. Otherwise, even with the very small LLMs, the noise may deeply affect the final answers. And if we want, of course, to add some other processes such as explainability and so on, it's better to have very structured and as small as possible pieces of chunks that fit the context. That is why this step of retrieving the chunks and a relation to be really optimized. So now let's talk about the key partnerships, Qdrant and Neo4j. So just a few words about the Qdrant. So we had different candidates, but Qdrant really stood out because it enables a simple deployment. It has a very, very low latency, and it enables to perform some other interesting operations, such as, for example, payload indexing. Neo4j and Qdrant, however, have a different paradigm. Sorry. Neo4j relies on ACID. It's transactional. It has a data integrity. And it supports rollback. Meanwhile, Qdrant is non-transactional and does not support any rollback. It's rather, as I've said, optimized for low latency search. So basically here, if Neo4j fails during this transaction, after Qdrant has already been updated, there is an inconsistency. And since, we have to deal with all these concurrent ingestion process, and this, of course, increases the complexity. So here's a bit how we will take care of this. So this is really during the ingestion process that what I'm here presenting is used for. We have to prepare a batch. So we first prepare some snapshots of Qdrant points before updating them. We first update them like optimistically. And now, well, if the transaction by Neo4j is successful, everything is in sync, this is perfect. Otherwise, if there is a failure identified, we will need to roll back to the snapshots that we previously saved. And afterwards, there will be a conflict resolver that will make sure everything is merged and the sync is preserved. So this is a bit quickly how it is performed during our ingestion mechanisms. And this enables to write across both systems concurrently. And also we have a very important here a notion of lineage metadata. We want chunks to be really aligned with both databases. That's why we take care of this sync dilemma. There were some elements here that were supported by Qdrant, but not Neo4j. So here an example is the nested payloads that was addressed by Qdrant. We just tried here to unify this during the ingestion, so by flattening the data in order to ensure the compatibility between both systems. In terms of performance, we had like very low latency performance, even with the expansion during the generation. Some reasons to this, we noticed that in Qdrant it was relevant to use a frequently filtered payload fields. And we also perform a separation of data with hot tiers and cold tiers in order to speed up what was frequently which was actually kind of a cache, and it was also providing some good speed up during our process. And the other one, of course, is the gain of accuracy of 20%. That was really improved with this graph notion compared to a classic vector database with whom we kind of compared our performance. This was measured by our team of linguists with manual annotations and blind manual annotations. Also, the enhanced explainability was clearly shown by handling graph data compared to chunk data that can be, as I've said, really big and a bit noisy also. The latency, well, I already said it. So yeah, here are the 3 points that were really comforting in this approach. So to conclude here, so as I've said, at Lettria we built a hybrid graph system. We first started with a vector RAG system. It was only using chunks and not any graph structure. By comparing our solution with one of the top vector RAG in the market, we noticed 20% of gain. We measured 20% of gain. It was pretty cool. Also, by using Qdrant as the vector database, we really simplified the deployments. It's really well compatible with this hybrid search. This hybrid search, of course, adds some dilemma to be solved, but as I've just shown you, it was pretty possible to fix them, and thanks to this conflict resolution functions. And what is important here is that we managed to preserve this lineage metadata. And this is at the origin of a lot of explainability in our answers, which is pretty satisfying for a client. Yeah, some other features, Qdrant, like a payload index or hot and cold data separation, also managed to improve the speed and the cost to reduce the excessive resource overhead. At Lettria, we are structuring the knowledge, and this will be the final slide for this 50-minute presentation, which is pretty short, I admit. So we structure the knowledge for smarter agent, smart application, let's say it. Neo4j really enables to graph, really enables, advanced graph building and retrieval. Well, we have already 15 graph enthusiasts, 10 million in funding, 20. We are graph enthusiasts. We are 15 graph enthusiasts. At Lettria, 20 enterprise customers, and we have just fine-tuned our Persus model that enables to build a graph with using an ontology, which is particularly remarkable as it outperforms some major LLMs on text-to-graph test. And this is done. So thank you for your attention. And well, I have to go now, but I will come back to the questions if you have any questions to ask on the days. Thank you very much.